All right, let's start here by talking about today a little bit about these so-called maximum and minimum values. What I have graphed for you there on the handout is a nice little function, 3x to the fourth minus 16x cubed plus 18x squared to be exact. So what I wanted to talk about here are these what are called relative or local maximums and minimums. And those are kind of the layman's terms for maximums and minimum. Local maximums and minimums are the peaks and the valleys. A good way to also refer to them. So that's what we're talking about here. Local maximums and local minimums. And the local maximums are the so-called quote-unquote peaks. And so one local maximum I can see right here, wouldn't you? It would be right there at x equals 1. That is a local max. What that basically boils down to is it's a maximum, not for the entire function, but it's a maximum locally speaking, around that point, right? That's a maximum point on the graph, around that particular value. So it's a maximum in that regard, a maximum function value. All right, so with that in mind, then, what about local minimum, you think? Well, the local minimums are going to be, so the local maximums are the peaks, and the local minimums are the valleys. And there are some limitations to that, to those words there, because that's not necessarily always the case, that a local minimum is a valley or local maximum is a peak. But anyway, it's for the most part, it's a good way to think of it. But what do you see? Local maximum right here. Local minimum at 0 and a local minimum there at x equals 3. And so those are the local mins for this particular function. So that's what they are for a basic standard function, and there's some other issues that we'll talk about in just a second, but that's a nice intro into it anyway. Let me also mention these are also called relative. You might sometimes see them referred to as relative max or relative minimum. Means the same thing. Local max is a relative max, and local min is a relative min also. All right. Now, also, here is a little bit of notation. How are we going to write that? Because of various things, we are wanting a specific way to write these notationally speaking. For the local max, we're going to use the function notation. And since we're talking about f of x here, the local max, now the maximum value we're talking about is the function value. And so the local max here is f of 1. And in this case, we just so happen to know that if we plug in, right, I've got it on my paper anyway, this point is 1, 5, so if we plug in the x to be 1, the y would be 5. You won't always necessarily have to know that, but we do here. And if you don't know it and you need to know it, you just plug in x to be 1, and that's how you get x to be, f of x to be 5. But that's the notation. F of x equals the y value. That's how we'd like you to write these local minimums and maximums. And so what about our local mins there? How would you describe those? This first one's the one on the left, be the easiest one, since we can see there. It'd be f of what? F of 0 equals 0, right? The x is 0 and the y is 0 there, so f of 0 equals 0. And what other one? Well, it'll be the one at f of 3, right? It'd be the function value at 3, which if you plug in 3, you get negative 27. So this low point turns out to be there, negative 27. Okay? Not too bad stuff, right? Okay, one other term here to mention. The combination local max and local min, those are referred to as local extrema. So if you see that term, it's just a way of denoting, if you say what are the local extrema, that's just a short way of saying what are the local maximums, what are the local minimums. They want both, okay? Local extrema. All right, so I think intro-wise, now as far as definition goes, here's, do I have enough space here? I think so. The definition of a local max and a local min is this. A function f has a local max, local maximum, at C if f of C is greater than or equal to f of x when x is near A. Here's near C, I'm sorry. A function f has a local max at C if f of C is greater than or equal to f of x when x is near C. Okay, well, what that means is our C value here in the case above is 1. That's C. That's where we're saying our local max is at, the x value. And doesn't that make sense? Don't we have that the function value at 1 is greater than or equal to, we'll talk about that maybe a little bit, is greater than or equal to every function value around it. So if I go at 0.9, then the one at 1 is bigger, right? If I go out here to 1.2, that's near 1. The function value at 1 is still bigger. That's all that's saying. The function value at that particular value is greater than or equal to the function value near it. Okay? Well, guess what? And f has a local min if what? F of C is less than or equal to f of x with x near C. It's just reverse, right? If you've got a local min, like down here at 3, at x is 3, well, the function value at 3 is negative 27, but if you go near 3 at 3.1 or at 2.8, wherever you go there, the function values are all greater. Or the function value is less than the one at C. That's all that's saying. Okay, so that's definition-wise how you do it. Just means that the function values for the local min, that local max has a function value greater than the ones around it, or equal to, and then for local min, the function value is less than the function values around it. That's what that's saying. With me? All right. Now, let me also mention here, before we go to that next one, the idea of the absolute max And absolute min? Well, an absolute max is this. It's the largest function value over the entire domain. Or specified domain, if it's restricted domain. And on the, this one's not a good example for absolute max, because if we go back to the one example I have here, we'll see some more later on, but does this one have an absolute max? Well, the absolute max is the largest value for the entire domain. And since these values, these values go up and these values are headed up, that graph just continues going up and up and up. So there is no absolute max on this graph. Even though we have a local max, there's no absolute max because there's no greatest function value. You with me? Absolute max means it's for the entire domain. No, we won't put infinity. That's right. However, on the absolute min, guess what it is? The absolute min is the smallest value, smallest function value. I forgot value here. The absolute min is the smallest function value over the entire domain or specified domain. And so what in the one there above example does have an absolute min, doesn't it? The absolute min on our example above here is f of 3 at negative 27. So the absolute min means for the entire thing, for the whole domain, not just an area around it. So yeah, that's the lowest value, function value, that any of these values has. With me? It's the lowest value. There's not a function value below negative 27, so it's the absolute minimum. Okay. Just thought I'd mention that. All right, now, on number 2 there, which got a little scribbling there, so let me see if I can erase that. And then get back to my pen. Okay. All right. So let's look at, so you can kind of see, that one, how, on the first one, how it looks. What about number 2 here? Well, let's first of all talk local extrema. What are the local maximums here? Well, again, since it's graphed off the graph here, this goes up and that goes up. Is there any point that is an absolute, a local max? Excuse me. Is there a local max there? I don't think so. There's no peaks. All right? Sometimes that's all you have to look for, but yeah, there's not any. Local mins, well, we got one, don't we? What local min do you see there? Right here, right? F of 3. F of 3 equals, looks like F of 3 equals 0, doesn't it? That's a local min. And then absolute max, well, there's none of that either. And then is our local min and also an absolute min? I do believe so. The absolute min is for the entire domain. And yeah, that's the lowest point on the graph. That f of 3 equals 0. Okay? One of the reasons I do that one is because this is a little bit different because it's a corner. And we'll speak to that more in just a second. But local maximums, local minimums can also be corners. They don't have to be, rounded off sort of things. Okay. All right.